In 2012, nearly 100 people were affected by a Legionnaire's outbreak in Edinburgh, with unfortunately lives even being lost. The culprit thought to have been water cooling towers hidden in plain sight. Now, if these structures are unregulated or even illegal, how do we even begin to find them? And if we can, how do we ensure a fast response? Hello, I'm Tadi, and I've been working with the UKHSA in using computer vision for disease surveillance and response. So as I highlighted earlier, rapidly identifying health hazards is crucial for disease response. These can be things like water cooling towers, or the focus of my project, car tire dumps, where disease-carrying mosquitoes can harbour. Now, manual surveys are simply far too slow, expensive, and impractical, especially for large land areas. However, with the advent of high-resolution aerial imagery, we can capture a bird's-eye view and utilize computer vision to automate the detection of health hazards. So what does this classic computer vision pipeline look like? Well, we start with collecting data, in this case, images of car tire dumps. We then train a model that learns what these images look like, and then we can apply this to an unseen image to identify where they may be. However, there are a few problems with this approach. First, that there's a lot of human effort involved in collecting the data and also labeling it. Secondly, for new objects, let's say water cooling towers, we have to redo this pipeline. We have to gather new data, we then have to train a new model. And finally, this becomes quite computationally expensive, especially if we keep wanting to do this for new objects. With these factors considered, if an emergency outbreak does occur, we may be too slow to respond. So during my project, I thought about these three aspects and maybe looking at this problem from a slightly different perspective. And in doing so, I used embeddings and image search similarity. So before I dive into embeddings, let's talk about images. So images are basically high-dimensional data. We have tens of thousands of pixels providing visual information as to what we are seeing. I used a pre-trained model to essentially preserve these semantics of what we're seeing. And what I mean by this are things like the color and the texture and the shapes that we can see. And this pre-trained model condenses this high-dimensional data into a much lower one, specifically numerical representation that we call embeddings. And we can also express this as a vector as well. So why is this useful? Well, in this representation, what we find are that images that actually look similar to each other lie close to each other in this representational space. What this means is that if I want to find images that, say, look similar to car tires, I only have to look for nearby embeddings. So let's look at this in action. So we begin by taking a location, and we take an aerial snapshot. We then divide this into patches, and for each patch, I embed it, and then I add it to a database. And the fantastic thing here is for each location, I actually only need to do this once. Now, if I want to find images that, let's say, look similar to this tire dump here, I simply have to embed it and search for nearby embeddings or search for similar embeddings. This allows me to quickly retrieve images and how similar they are to my initial query image. And it's fantastic because for new objects, I simply have to embed it and then query it. And this cuts down the human effort in gathering data massively. So let's say I have two locations and I want to identify where my tire dumps are. Well, as I already have my images embedded, I simply have to query my images and I can locate precisely where they might be. So to conclude, I've been using embeddings and image search similarity as an alternative pipeline for identifying public health hazards. I've shown that actually we have a massive reduction in human effort, with data gathering being at least 100 times faster. This approach is efficient and scalable as well. For new objects, we don't need to retrain a whole new model, cutting down image processing from weeks to hours or potentially even minutes. And finally, if there is an outbreak, you can have a fast and adaptive response, cutting down a response time of weeks to hours, meaning that we can locate and rapidly identify public health hazards.